By the way, so in the first exam you have done a bad thing, which is okay. So what I would like to suggest, or at least tell you, that is still you have a chance. So because you are all bright people, sometimes misguided by different kind of people, so you don't know what to do. I am giving you one more chance. So if in the final exam, which will again 4 questions, 40 marks only, right? If you can score 40 out of 40, if you can score 40 out of 40, I will give you AA grade irrespective of your performance anywhere in the course. Okay, so you have a chance. Okay. Okay, so briefly, I'm going to talk about how to approach the quiz problem. I will give you a sample thing, and I think that will tell you how to approach this. Okay. Some of the problem was difficult, of course, for the ring ones were the difficult ones, but anyway. So if you have ax square plus bx plus c is equal to 0, I'm just taking a simple example, say z2. If I give you this for z2, you know that there are 4 cases, right? I mean, 4 equations, because A is not equal to 0, so B has 2 choices, C has 2 choices. So other equations are easy, right? For example, x square is equal to 0. You know what are the roots? 0 is a double root there, right? Then x square plus 1 is equal to 0. X equal to 1 is a root. Again, this is a double root, right? What else? Any other equation? X square plus x plus 1 is equal to 0. And one more? Huh? X square plus x is equal to 0. Now you see that this is a trivial case, this is a trivial case, this is a trivial case, right? Because in all these 3 cases, here 0 is a double root, here 1 is a double root, and here x is equal to 0 and x is equal to 1, right? So it's easy to solve in these 4 cases. This case is a little bit non-trivial, but you know that we have constructed field with 4 number of elements using this equation, right? So essentially, I can write it down roots of this equation as x minus alpha into x minus alpha square, where alpha square plus alpha plus 1 is equal to 0. So roots of this equation are alpha and alpha square with this condition satisfied. So that means they are outside the Z2, right? They are outside the Z2. Same approach, just like that from reals. If you take equation x square plus 1 is equal to 0, on reals, roots are complex numbers, right? So it is in the complex plane. In the same manner, these roots alpha and alpha square are in the outside of Z2 or GF2. They are in the ZF4 field with 4 number of elements. Same approach you have to do for all those 4 questions with Z3, Z4, Z5, Z6. Z3 and Z5 are easy because they are field case. Okay, so you should be able to do it easily. In the case of ring, it is a little bit more non-trivial. So, I mean, that is a luck who got what question. But anyway, that was a difficult thing. But anyway, I have given only 1 or 0 in quiz, right? So it's only attendance. I have not worried about your, because I know that you will not be able to solve, right? Anyway, so that is okay. So I hope if any of you can still, I invite you to solve it completely for any of those 4 cases. Show me the complete solution, right? So you have to make cases, and you have to basically make cases such that in certain cases roots are within the ground field, in certain cases roots are outside the ground field. Okay, and so you have to figure it out what is happening. Okay, so good cup of tea you will require, right, and a coffee to sit down and do it. Okay, got the idea about quiz? So I hope you know about it. Okay. Now, Now I'm going to tell you something very beautiful, and that topic is how to remove wrinkle on your face. Okay. So I'll start with that. So basically, yes, what? Z6 also the approach is same. In the case of ring, approach is same. Only one thing you need to remember, because this is degree 2 equation. So over the fields, degree 2 equation will have only two roots. For example, you saw x is equal to alpha and x is equal to alpha square is only root. Okay. But in case of ring, it could be more than 2. That is the beauty of ring actually, yes, right? So you need to look at it, do some calculations and see what happens. Okay. Anyway, this topic, so I'm going to talk about what is known as matrices, right? Which is a very popular topic. But before talking about matrices, let us see a couple of applications of matrices, because we should know where they are applied, you know. And so you will see this course, algebraic structures used to happen, but I think now they have changed it to linear algebra or something in your course curriculum somewhere. I don't remember what they keep on changing, but anyway, the heart of engineering is this equation: Ax is equal to B. You saw that equation? A is a matrix, X is a column vector, and B is a column vector. So any engineering problem you do, it reduces to bunch of these equations, okay? And once you have these equations, you should know how to solve them. And certainly, matrices are very, very important. Those machine learning lovers, you know, they should know that without matrices, you cannot do anything, right? So the linear algebra and these things are very, very important. Anyway, even this, you know what is this? This is Pioneer 10 spacecraft, which is far beyond our galaxy. I mean, it is outside our solar system actually. It went long time ago. And also it is emitting what? Value of pi, for example. Because if aliens are there, they can identify pi. Okay. They can only, you can only talk to aliens in terms of mathematics. There is no other language. So value of pi or other things, you know, and many other interesting things anyway. This is a Mars rover. So how these communications, deep space communications are controlled? They are controlled through a beautiful branch of mathematics and computer science and electrical engineering known as coding theory or error correcting codes. Okay, they are very, very powerful mathematical algorithms which correct errors whenever we are sending information from one place to the other place. Okay, so for example, if I am talking to you and if you are not able to understand, so you will say that please repeat. So repetition is a crude form of error correction. Okay, and this is inbuilt everywhere in the engineering or everywhere wherever there is information processing, whether you want to store data somewhere or whether you want to transmit data from one place to other place, these algorithms are used here. Okay, and these two books you should read. You must have these two books on your table. Even if you are engineering student, computer science student, doesn't matter. Hoffman, Ray Kunz, linear algebra. As soon as you learn these things, you can do a lot more wonders in machine learning, as I mentioned to you. And then abstract algebra by John B. Fraley. So you should read this as a mathematical part. I am telling you what is important. Okay, but not for this course. But you know, if you are really loving mathematics, then you can look at it. And there are some supplementary books. This is a quite celebrated book, Ian Hustine, Topics in Algebra, and it will challenge your brain, right? So if you love to do exercise for your brain, you can try to solve the problems of this book anyway. So as I mentioned, any science, engineering, in business problem ideas leads to system of equations. Equations are everywhere. So what are the applications? Space and satellite communication, data transmission, data storage, digital audio, video transmission, mobile communication, cloud computing. Everything is there, okay? These are some applications of coding theory. And of course, cryptography, security, crypto system, network security, cloud data security, homomorphic encryption, and so on. Signal processing, digital signal processing, image processing, signal and systems, speech processing, VLSI, wireless communication. You pick up any topic. It's such a powerful thing, right? So now let me show you how to remove wrinkle on your face. So I am again taking slides from, not from Professor Bush, this time someone else, okay? Professor Gillette, okay? Anyway, so digital image is nothing but a matrix of numbers. I think if you know MATLAB, probably some of you know MATLAB. Okay, so you might have seen. I think these days people learn MATLAB in high school, right? So, oh, you are busy with JEE, I know. So you have not seen the real beauty. Anyway, so any image correspond to bunch of these numbers, pixels. So there are numbers here, Basically, an array of numbers is known as matrix. Okay. So from numbers to images. So if you type these numbers and color them, so 1 is black and 8 is white. So the rest of colors are in between. You will observe this pattern. If you use MATLAB, you can see these kind of connections. On MATLAB, it is easy to see. Okay. So 1 is dark and 8 is white, and everything in between. So basically, one more time, if you take powers of 2, so 1 is black, 128 is white. Rest of colors are in between. You see the pattern like this, that corresponding image. Okay. So let us compare these two. Okay. So these are the numbers which simply increasing by 1, and these are powers of 2. You can see the difference in the image that you obtain. Okay. So from an image to its numbers, so if you look at this image on the right hand side, okay, it has 200 into 320 numbers. You can zoom it, say 40 into 50, 40 rows, 50 columns, right? To further zoom it, one portion of it, another zoom. So basically, if you take a small portion of it, zoom in the middle eye of image 10 by 10, it corresponds to this. And now these things can be converted into numbers. I mean, for understanding purpose, you can use MATLAB. MATLAB is having all these commands. You take the image and you can actually do whatever you want to. You can get the numbers from that. So basically, this is the middle eye of the image, 10 by 10. And the corresponding numbers are this. You see? So the rule is bright color, high numbers, dark colors, low numbers. Okay, these are some numbers for that. So essentially, whenever we are dealing with images, we are dealing with numbers, array of numbers. So now, if you average the numbers, you are actually smoothing the images. So idea is, actually, let me show you. These numbers are there, right? I take this portion here, say, and I take average of these numbers and replace with 2. This is there, right? The red portion. So pick a pixel there, look at the number, look at the neighborhood, and just do the average of the numbers and replace the middle one. You can do this easily. These days softwares are there which can do these things for you easily, right? So that way you can smoothen the image, right? You can see that if there are wrinkles, you do this averaging in the neighborhood of those points and the wrinkle will be removed, right? Okay, so this is a one nice application of matrices. Okay, another one in deep space communications. You see, this is a picture of Mars taken from a spacecraft. Early it was 1965. This was the standard of the communication technology. You see how hazy pictures taken by this spacecraft. Later on, actually, I mean, it took about 8 hours to transmit this picture, basically. If you use error correcting codes, the powerful algorithms, actually you see the clear-cut picture of the Mars. So error corrections are very, very important, and you can see that these kind of images can be obtained. So it is everywhere. Your mobile phone, computer. Without error correction, nothing is possible. And if you search on Google, right? Search on Google is the largest matrix computation that happens every time you fire a query. Okay. So again, bunch of questions are solved. Okay. You can look at this book actually. It calculates eigenvector. What is eigenvector and eigenvalue? I will tell you. Anyway, so origin of algebra, you can look at this book, Dance of Shiva, which talks about few things. Panini, Aryabhat, Chandashastram, Pingla, and this is for the algorithms actually. That's all for some applications, okay? Oh, I think I missed the slides anyway. Anyway, I think I missed the slide, so I have to go on my memory. If I remember, let me see how much I remember. Anyway. So matrices, so I hope you got the idea of matrices, right? Now let me show you an array of numbers, something like this. A11, A12, A1, and A21, A22, A2n, AM1, AM2, AMN. This is M row n columns, and normally we write it like Aij, M cross n, right? This is a matrix. Now, I think you know some of the topics like addition of matrices are possible, subtraction of matrices are possible. These Aij are numbers. You can assume they are either real numbers or complex numbers, something like that, right? So you can do addition, subtraction. You can multiply with a scalar lambda. You can multiply the whole matrix. These operations you can do, right? You can also compute determinant, right? So what is the formula for computing determinant of n by n matrix? N by n matrix. ठीक है, चाय पे सोचना. N by n matrix. How will you find determinant of n by n matrix? So something you can look at it anyway. The formula will involve what is known as some sort of permutations. Okay, will require some permutation function. So I hope A is n by n matrix. Okay, so now I'm going to tell you something. So I think all the other basic things are probably I'll skip because I think we have a lot more properties of matrices, right? I'm skipping all those things. Probably you can watch the last year lecture because it's something elementary and you have done it. I'm going to talk about something interesting, what is known as eigenvalue. Have you heard of eigenvalue? Eigenvalue? No? Okay, let me talk about the eigenvalue and why they are important. Eigenvalue and eigenvectors. So eigenvalues was of course invented by Mr. Eigen, right? So that's why the name eigenvalue. If you go to a hotel, right? Suppose you go to a 5-star hotel and you go to bathroom, right? Washroom. And then there is a, bathtub. You see there is a, you can actually turn around the tab on the right hand side. Water is too hot. On the left hand side, it's too cold. So what is this system? And sometimes it is difficult to maintain the temperature, right? This is the kind of system. And, we can talk about the stability of the system. And stability of any system actually can be you can describe in terms of these eigenvalues of the corresponding matrix. Such a beautiful concept, right? So basically, eigenvalues are very, very important. Okay, so let me show you what are the eigenvalues and how to compute them. If A is A, B, C, D, I am taking a 2 by 2 matrix. Okay. Or, I mean, okay, let me give you the definition in general. Suppose A is a n by n matrix. You take a matrix A, multiply with a column vector X. So this is basically, this is the matrix A, this is X. This is a n by n matrix, and this is n rows, one column. Take a matrix A, multiply it with a non-zero column vector, and if it turns out that it is some multiple of X, then lambda is known as eigenvalue. Remember, X is a non-zero vector. Okay. So you take a matrix A, multiply it with a non-zero vector X. If it turns out that Ax is equal to some multiple of X, lambda times X. Lambda is a scalar number, right? It could be real or complex, whatever, right? So basically, then lambda is known as eigenvalues. Okay. And this non-zero X is known as eigenvector. Okay. The eigenvalues are very, very important for matrices because they represent some sort of systems. When systems are represented by transformations or something, okay. So you will look at those things probably in your signal and system course in future. You will see those things in more detail. Okay. So let me give you an example. Okay, so 2, 3, 0, 1. What are the eigenvalues? Can you find it out? So what we do actually, see, so from this expression, I can say that A times A minus lambda times I times X is equal to 0. Do you agree from here? I is the identity matrix, right? We can I've just recalculated everything. So A minus lambda I is equal times X is equal to 0. Now X is non-zero, so this will have a, non-trivial solution if we have the determinant of A minus lambda I is equal to 0, right? So this is our equation known as characteristic equation for finding the eigenvalue. Determinant of A minus lambda I. So you just solve this, you will find lambda. Once you find lambda, you substitute Ax equal to lambda X and solve for X. That will be the eigenvector. Got it? So let me do an example for you. For this matrix, what are the eigenvalues? Can you tell me? हाँ कौन बोला? कोई तो बोला, सही बोला. हाँ. Q1 and 2. कर लिया? Very good. You can observe that 1 and 2 is here in the diagonal. Why? Because the matrix is upper triangular, right? Yeah, upper triangular. The lower portion is 0. So if matrix is upper triangular or lower triangular, diagonal has eigenvalues. So beautiful thing, right? When you compute eigenvalues, right? So you can actually compute. Just write down A minus lambda I, right? Determinant of A minus lambda I, you can compute, right? Or maybe I can give you a formula. If A is A, B, C, D, A minus lambda I will be A minus lambda B, C, D minus lambda, right? So determinant of A minus lambda I is equal to 0 will give you A minus lambda, D minus lambda minus BC is equal to 0. When you simplify this, what you will get? Lambda square minus trace of A, trace is the sum of the diagonal elements, plus determinant of A is equal to 0, right? Directly got a formula for computing the eigenvalue in case of 2 by 2 matrix. Okay, got it? So I think you can see that we have AD minus A lambda minus lambda D plus lambda square minus BC is equal to 0. So in other words, we have lambda square minus lambda square minus A plus D times lambda plus AD minus BC, right? AD minus BC is equal to 0. This is known as trace of A and this is known as determinant of A. So in case of 2 by 2 matrix, you know the formula. For higher things, it is difficult. Finding eigenvalue and eigenvector is a costly business. So it requires computer science and difficult thing too. But whenever you fire a query, so basically, this on Google actually, so Google uses these kind of heavy computations, at the back end, anyway. So all kind of things are there. So it's a beautiful thing, so how these things are useful in a variety of places. Okay, so this is the eigenvalue computation. Once you know the eigenvalue, so for example, in this matrix, what will be the eigenvalue? 2301. By the way, this I am giving you everything over reals. I can consider over complex. I can consider over Z2. I can consider over Z4. Things will become more beautiful, right? So you have the domain in your hand. So when you solve system of equations over finite fields, as it was done in 1912 by Ramanujan. Ramanujan, Ramanujan solved a system of equations over finite fields in 1912. And G.H. Hardy, who was a famous mathematician, told, you see, the kind of work that we do means myself and Ramanujan has no application. This is just beauty of mathematics, right? It turns out that around 77 or maybe something like that, uh, BCH code, Bose-Chaudhary-Hockingham code, BCH code was discovered, and decoding for correcting the errors, and they are known as mother of all codes actually. So all these beautiful codes that you see for correcting errors, they're all coming from BCH code. And when you solve BCH code, actually you want to decode something, you exactly get the same system of equation which Ramanujan gave in 1912. So you see the beautiful connection. तो आज जो बेच नहीं सकते हो उसको कल बेच सकते हो, right? So when you want to sell, it is up to you and how you want to sell. Okay, so it turns out that it's a beautiful connection that was discovered anyway. So system of equations over finite field is a really tough task, by the way. Anyway, so that's about eigenvalue. How do we find eigenvalue and eigenvector? So what are the eigenvalues here? So 2301. If I write down, A is equal to 2301. So then lambda 1 is equal to 2, lambda 2 is equal to 1, right? You can find it by solving this equation. You can do that. Now, if I have to find the eigenvector, so I look at A times, so basically A times X is equal to, say, lambda 1 times X. A is 2301, X is x1, x2. Lambda 1 is say 2 times x1, x2. Can you solve this for x1, x2? Right? And that will be your eigenvector for a given eigenvalue. So eigenvalue, when we took eigenvalue 2, we got one system of equations. When we will take eigenvalue 1, we will get another system of equations. So 2 eigenvectors you can find. And there is a beautiful relationship between lambda 1 and lambda 2 and the corresponding eigenvectors. That I think you will look into those things in your आगे आने वाली classes में, right? Linear algebra. I am not teaching that. I have taught it only once. But anyway, that's a beautiful connection you can see later on, right? Okay. So, I mean, what questions I can ask you, for what relationship between lambda 1 and lambda 2, these vectors, eigenvectors, you get 2 eigenvectors, right? When they are orthogonal. See, that's a beautiful question to ask. Exam में question पूछने में आसानी होती है, right? So then you have to think anyway. So that's a eigenvector. You can find out how you can find eigenvector. I hope you know. You can solve. I'm not solving this anyway. It's a very trivial thing. And in fact, if you want to know more details, I have already done this in my previous lectures. You can see something easy. Anyway, so that's all about eigenvalue, eigenvector. I have another beautiful thing to tell you. And as you know, there is a shloka, right? Yatha shikha mayuranam naganam madiyotha todedang shastranam gaditam murdhani sitam, right? So mathematics is queen of all sciences. So if you look at the queen, so what is the so basically crown of the queen is which subject in mathematics? You know? So mathematics is very vast, so many things. Which subject is the crown? No, not calculus. By the way, I should tell you, mathematics, there are 4 pillars: algebra, number theory, geometry, and calculus and analysis. There are 4 branches. Which one is most beautiful? Number theory. So the crown of the queen is number theory. Now you go one step further. What are the gems on the crown? So gems are nothing but what is known as quadratic residues. Beautiful thing. And those quadratic residues are very powerful. Actually, Gauss has done a lot of work on it. Paul Frederick Gauss, you might be remembering. So let me show you about. So these quadratic residues are so beautiful thing that using this, see, if you want to create some beautiful thing, you have to take some beautiful thing, right? So you take quadratic residues, and I am going to create what is known as Hadamard matrix. Another beautiful thing. And Hadamard matrix are very useful. For example, in quantum computing, Hadamard gate is there. Uske bina kuch hota nahi hai. Similarly, you know, in optics, we have plenty of applications of Hadamard matrix. They are beautiful matrix. Okay. So first, let me tell you about Hadamard matrix a little bit. Then I'll go and show you how they can be constructed using quadratic residues. So what are quadratic residues and how we can construct them? So these are square matrices. H is the n by n matrix with entries to Hij plus 1 minus 1. Entries, suppose plus 1 and minus 1 ले लें. So these matrices are such that H transpose is equal to Ni. H transpose is equal to Ni. All these matrices with entries plus 1 or minus 1 are known as Hadamard matrices. Okay. So you can see that I have taken alphabet as plus 1, minus 1. But as you know, I love to change this to Z2 4, GF4, and all variety of things you can do, right? So basically, that is in your hand to look at those kind of Hadamard matrices. By the way, so once we talk about Hadamard matrix, we have to talk about Hadamard lady. There is a Hadamard lady. Okay. So let me show you. I met her long time ago. I think in 2001 I met her in New Zealand actually. So I think Google will, yes, Hadamard lady. So Hadamard matrix lady, mother of cryptology in Australia, the grandmother of computer security. Anything in security or cryptography has to go through her in Australia, you know. She's very powerful in cryptography. And she's also known as Hadamard matrix lady because Jennifer Sabri, she has done a lot of work on Hadamard matrices. Okay. So I think she's retired now. If you see her home page, you can you see matrices somewhere? Yeah. These are matrices, you see. Hadamard matrices of certain size. Another Hadamard matrix. So plus one or minus, so minus dash means minus one. So plus one and minus one, right? And how you can search for Hadamard matrices? You can search through computers. And soon you will realize computer is the idiot box. It cannot do much. I think the last was 420 or something, which is still open case. So I think some exercise I have given to you in your assignment to actually search, then you feel the beauty of computers that they cannot do much, right? If you really want, yes. Just the beauty, to understand the beauty. So basically, you see, they have wider applications, you see. So there are so many applications of Hadamard matrices, right? I'll show you, right? They are useful in cryptography, they are useful in security, in quantum computing, variety of places, in optics, physics. Okay. But why people want to study, you know, मैथमेटिशियंस को चाय पे कुछ चाहिए एंजॉय करने के लिए तो एक मैट्रिक्स ले लिया देखिए इसका क्या होता है राइट so let me show you some beautiful stuff of Hadamard matrix. Okay. So if I ask you example of a Hadamard matrix, the first one that you can do is this. One, one, one minus one. Right? This is a Hadamard matrix. Can you, or I think with the scaling factor of 1 over square root of 2. So you can check what is HS transpose. Can you tell me? 2 1. So again, Hadamard matrix. Right? This is also known as Hadamard gate in quantum computing, very famous. If you know about quantum computing, so then you might be recognizing it. Okay, so this is 2 by 2 matrix. What about higher size? 4 by 4. What about 4 by 4? So what I'm going to do actually, I'm ignoring the scaling factor 1 over root 2, but you can actually include that. If you so this is 2i. If I take 1 1 1 minus 1, take tensor product with 1 1 1 minus 1. Do you know what is tensor product? Take each bit here. Take each bit here expand it with whole matrix. So 1 times whole matrix, 1 times whole matrix, 1 times whole matrix, and minus 1 times whole matrix. So this will be something like 1, 1, 1, minus 1, 1, 1, 1, minus 1, 1, 1, 1, minus 1, minus 1, minus 1, minus 1, 1. Another Hadamard matrix. Right? This is another Hadamard matrix, you see? 4 by 4. So what is the real beauty about this matrix? If you take 2 rows, take the inner product, it is 0. If you take 2 columns, take the inner product, it is 0. So rows and columns are orthogonal to each other. That is a beautiful thing, right? Can you see that? Rows are orthogonal, columns are orthogonal. And matrices with first row is all one vector is known as normalized Hadamard matrix. Normalized Hadamard matrix when the first row is all one vector. I have not put that condition initially, but it's easy to play with if you have first row as all one vector. Okay. So question is, if I ask you to find different Hadamard matrix, how will you approach this problem? Yes, any computer science, competitive programming people, right? Who are expert in competitive programming, how will you find these matrices? I mean, if you think you are very good, you can actually get some prize also. And also, because I think these matrices are known only up to certain values of n. Earlier it was 92, then they extended it a bit further. I think some, I don't remember now at the top of my mind, but yeah. So people, if I look at the Wikipedia, you can see, okay, what are the values for which they have found. So basically, I have given an example to find Hadamard matrix by computational search. How will you find Hadamard matrix through computational search? Okay, you can find. So of course, these are very useful thing. Okay, so this is one way. If I want to construct, this is 4 by 4. If I want to construct 8 by 8 matrix, what I will do? Take this matrix, tensor product with this. Each bit is blown by 2 by 2 matrix. So you will get bigger matrix, right? And that way you can continue. So power of 2 you can get from here. Got it? So this is known as Pele type construction of Hadamard matrix. Just blow the matrix by a 2 by 2 matrix. Every step you get 8 by 8, then 16 by 16, 32 by 32, power of 2. Okay. By the way, there is a beautiful conjecture which is a still open problem for the Hadamard matrix. So this is again a T time problem. What is a Hadamard matrix conjecture? And can you throw some light on it? On one evening, maybe with a cup of tea. Why I say like this always? Because there are young people who have done like this, There was a problem which was 350 years old, not solved by even Carl Friedrich Gauss, was solved by 2 undergraduate students, okay, in one summer. So maybe I expect you can also solve, right? One such problem. You require fresh ideas anyway. Okay, so what is Hadamard matrix conjecture? That is a T problem, okay? Okay, so I think now I can talk about quadratic residues. Quadratic residues. Let us take P to be a prime, odd prime number. Primes are very beautiful, right? As you know, primes can actually show you different connections. Anyway, P is a odd prime. Then what you do? Suppose P is equal to 5. Suppose P is equal to 5. So what are the numbers less than 5? 1, 2, 3, and 4. Right? I take 1. I square it. 1 square is equal to 1 mod 5. I take the second number 2. 2 square is 4 mod 5. I take next number 3 square. 3 square is 9 mod 5 4. You are back here. Take 4 square mod 5. So see that when we are squaring and reducing it to modulo 5, we are getting only two numbers, 1 and 4. So these numbers 1 and 4 are known as quadratic residues. Mod 5. And the rest of the numbers 2 and 3 are quadratic non-residues. Got it? तो मेरे को बताओ p is equal to 7 के लिए quadratic residues कौन कौन से आएंगे? p is equal to 7 के लिए 1 होगा और 1, 2, 4 बड़ी जल्दी निकाल लिया. So 1, 2, 4 are quadratic residues, modulo 7, right? P is equal to 7, and rest of them are quadratic non-residues, right? Got it? So these are beautiful things. Yes, question. Huh? 0 is neither quadratic residue nor quadratic non-residue. हम just खाली 1 से ले रहे हैं, 1 से p minus 1 तक, by the way. So for a fixed p, I am looking at 1, 2, 3 up to p minus 1, and you can clearly see that half of them are quadratic residues, half of them are quadratic non-residues. Half of them are quadratic residues, half of them are quadratic non-residues, right? Okay. So that is a. One may ask another interesting question. Okay. There are some theorems known as Perron's theorem. Perron is a very famous person. That how when you add two quadratic residues, what will happen? When you add one quadratic residue and one quadratic non-residue, you will always get quadratic non-residue. All kind of theorems are there. Again, I am skipping the details. हमको एक lecture में पूरा खत्म करना है अभी 5 मिनट है 10 मिनट है, right? So that's why I'm skipping the details, but it's easy. Matrices are easy, right? So you can easily handle this stuff. So for p is equal to 7, you saw. Similarly, you can do for p is equal to 11. Now, is there any gentleman or any person who has this idea how to use these quadratic residues to construct the Hadamard matrix? Any idea? It's a very, very, very beautiful idea. Just think about it. How will you use these quadratic residues to construct a Hadamard matrix? Any idea? Okay, so I am giving you some hint, and maybe you should try. What you do? Suppose p is equal to some prime p. P is there, right? So this will construct a Hadamard matrix of size p plus 1. But anyway, how do you construct? Before constructing a Hadamard matrix of size p plus 1 for p prime, I am going to look at another matrix known as Jacob's Hull matrix. Okay, and that's another mathematician. What you do? You write down a p by p matrix. P by p matrix. The first row is, so suppose p is equal to 7. So let me do it for you. P is equal to 7. What are the quadratic residues? And quadratic non-residue? 3. So I am constructing a matrix. 1, 2, 3, 4, 5, 6. Sorry, 0 is also there. 0 is quadratic, neither quadratic residue nor quadratic non-residue. So I am putting 0 as a, every time I am putting a 0, so this is always 0 actually. Okay, in everything. 1 is a quadratic residue, right? Put 1. 2 is a quadratic residue. 3 and 4 is quadratic. Sorry, 4 is quadratic residue. Can you see what I have done? 0 is 0 because 0 is neither quadratic residue nor a quadratic non-residue, right? So I'm putting 0 there. 1 is 1. 1 is a quadratic residue, I place 1. 2 is quadratic residue, I place 1. 4 is quadratic residue, I place 1. Rest of the places it is 0. Right? Then what I do? I take a cyclic shift of this. So I write down this 0 here, this 0 here, this 1 here, this 1 here, this 0 here, and like that. Take another cyclic shift. So you will get finally P by P matrix. Right? Using this matrix, you can construct a Hadamard matrix. फिर भी अभी थोड़ा सा एक लाइन बाकी है. How do we go for P+1 matrix? इसी एग्जांपल से साथ प्ले करके देखो, right? What will happen? You got the idea? So I'm just writing here. This is 0, 0, 1, 1, 0, 1, 0, and this is 0, 0, 0, 1, 1, 0, 1. Then next 1, 0, 0, 0, 1, 1, 0. Then 0, 1, 0, 0, 0, 1, 1. Then 1, 0, 1, 0, 0, 0, 1. Then एक और होगी क्या? 1, 1, 0, 1, 0, 0. This is P by P matrix actually, 7 by 7 matrix. Okay, so now क्या 7 by 8 हो गया? साथ ही तो है ना 7 by 7. So I have taken the cyclic shift. Okay. इतना काम कर दिया है मैंने. अब आगे का काम थोड़ा सोचो, चाय पे, राइट? How do we construct a Hadamard matrix of size P+1? ठीक है ना? हालांकि सब दिया हुआ है, हमारे पुराने लेक्चर में दिया हुआ है, मैं नोट्स भी दे दूंगा, सब कुछ है, बट फिर भी थोड़ा सोचो ना. आई एम जस्ट ट्राइंग टू एक्साइट. I want to bring mathematician out of you, right? Who can solve these problems, right? थोड़ा सा सोचोगे कैसे करें? How do we, whether this matrix has this property that HS transpose is equal to PI? This matrix has this property? Check कर लो. You don't know. So, okay. Okay, so this is how the technique. So basically, take a beautiful thing to construct another beautiful thing. That is the property. Quadratic residues are beautiful and Hadamard matrices are beautiful, so you can construct them from beautiful thing. I think that's all. Another topic is about Fourier matrix again. That is okay. Fourier matrices are very beautiful again, but I think in the assignment I have given you the definition and I have asked you to find the eigenvalues, so which is easy. And for some of these Hadamard matrices, I have asked you to find the eigenvalues and eigenvectors. Okay. So I told you how to find eigenvalues and eigenvectors. So remember, for degree n, for n by n matrix, finding eigenvalues is a difficult task because solving degree n equation is there is no formula, right? Formula is available for degree 2, Shidrachar formula, degree 3, Cardan's cubic solution, पढ़ा है? और degree 4, degree 4 का पढ़ा होगा, degree 5 है ही नहीं. तो बेसिकली कितनी सिंपल चीज है एक डिग्री. और मैं तो डिग्री 2 इक्वेशन तुम्हारा Z2 Z4 पे पूछ रहा हूँ, उसका भी सोल्यूशन नहीं है, राइट? Z4 Z6 तो कर सकते हो उसका सोल्यूशन, बाय द वे. It's not difficult. Anyway, so I think that's yeah, that's all. So I think that's all for matrices. I guess that's right. Next topic will be algorithms. By the way, few things I have left, few details. You can look at the last year video. You know, you will be able to find that thing. You know, or lecture 14. I think it is lecture 14 probably, last year video, if I remember it correctly. Anyway, thanks.